Welcome to the hands-on workshop, Performance Optimization for Intel Xeon 5 Processors. This is episode 2. I am Andrei Vladimirov with Colfax International. In episode 1, we talked about Intel architecture and the role of Xeon 5 processors in it. Now we are beginning a module in which I will discuss the organization of Intel Xeon 5 processors from the programmer's point of view. In this episode, we will talk about cores and threads. Inside of every Xeon 5 processor, there are up to 72 cores. The cores are organized into tiles, and each tile has 1 megabyte of the level 2 cache. The slices of the level 2 cache belonging to different tiles are kept coherent by hardware. As the programmer, you don't need to worry about maintaining coherency. But you need to be aware of another aspect of this architecture. It is sensitive to data locality. That is because to maintain cache coherency, the chip uses a mesh interconnect. In this mesh interconnect, each vertical link and each horizontal link is a bidirectional ring bus. This bus carries address traffic and data traffic between the different tiles and also between tiles and memory. If your program can work in such a way that each core only talks to the local level 2 cache, this is going to be the ideal scenario with the lowest latency. If it needs to talk to a near neighbor's cache, this is going to give you greater latency. And finally, if you have to talk to a remote neighbor's cache, this is going to give you the longest latency because the traffic may need to make more than one hop. At the same time, this mesh organization is an improvement over the first generation of Xeon 5, because in Knight's Corner processors, there was just a single ring connecting together all of the cores. Now let's zoom in on one of the tiles. What we will see is 2 cores, and each core presents itself to the operating system as 4 logical processors, thanks to the 4-way hyperthreading technology. The purpose of this technology is to allow you to run 4 threads on each core, and you can overlap the utilization of different resources in time. For example, one thread may be issuing a long latency arithmetic instruction, and while it keeps the vector arithmetic and logic units busy, another thread can go in and use the memory controllers. To further pack the pipeline, Knight's Landing cores have out-of-order execution. Importantly, arithmetic instructions are executed on 2 vector ALUs per core. What these ALUs, arithmetic and logic units, do is they perform operations on short vectors. These operations come from the AVX 512 instruction set, and we will talk more about this in episode 3. But as a programmer, you need to be aware that there are 2 levels of parallelism in Knight's Landing. Cores can run independent streams of instructions on different data sets, and there are also vector units inside of every core that can run a single stream of instructions on multiple data elements. These 2 levels of parallelism must coexist in your application. To utilize multiple cores and multiple logical processors within a core, you will need to use threads, and for that purpose you will probably need a threading framework such as OpenMP. And then inside the code of every thread, there has to be vectorization so that a single stream of instructions may be applied to multiple numbers at a time. These 2 levels of parallelism are called MIMD, multiple instructions, multiple data, and SIMD, single instruction, multiple data. This organization of cores and vector units is common across all Intel architecture processors, including Xeon 5, second and third generation, and Xeon. But if you compare second generation Xeon Phi with first generation, you will find significant improvements. Second generation Xeon Phi cores are based on Silvermont architecture. As a consequence, they have out-of-order execution, and this gives you better latency masking. They can issue back-to-back instructions from a single thread, so you just need to run one thread per core to use all of the resources. This is different from first generation, where you had to have 2 threads per core to use every cycle. And branch prediction is also improved in Night's Landing. This allows you to waste fewer cycles in speculative execution. Generally, you can say that second generation Xeon Phi processors are more forgiving to non-optimized code. At the same time, these cores definitely benefit from performance optimization. In episode 3 of this workshop, we will talk about that second level of parallelism, vector instructions. Stay tuned.